Okay, it's a real pleasure to be here. Generation 1 planets. I made up that word. Okay, why do I make up that word? Let me explain what I meant by those words. Okay, this is the Astro 101 picture you would show to your excited undergraduates about how planet formed in the solar system. At least we have two kinds of populations. Two populations of planet. One is over the outside, the gas giants, because they have a significant amount of hydrogen helium on the outside. It's thought, reasonably, that they were formed very early on when they were still embedded in the gaseous disk. And that's what I call Gen 1 planets. And in the interior of the solar system, we also have the terrestrial, 4 terrestrials. They are low mass, small, bare core. They don't really have a substantial amount of hydrogen helium, substantial amount of atmosphere. So the theory currently is that they were formed after the gas disk has gone away. We don't know that's true, but let's call that Gen 2 planets. So I made up these words because it makes it much easier to write proposals. People know what's Gen 1, Gen 2. You don't have to keep on saying those names. Okay. In this story, there are also a couple other ingredients. Okay. There's also the ingredient so-called Iceland, which I'm sure you all heard about. There's this place where water, outside which water, which is one of the major metallic reservoir, can condense into solid form and therefore can form into cores of planets. And the story goes that if you are outside the Iceland, it's much easier to form cores of giant planets. And observationally, that seemed to be confirmed to some degree. Oh, yeah. It helps when you're short, so I can hope. Observationally, this is confirmed to some degree because whenever we see gas giant planet, in this case Jovian planets, they do seem to spike up very steeply outside certain distances, in this case about 1 AU. So there's some truth perhaps to that magical distance. That magical distance also, there's another implication to it, is that if you do have more metals in the disk, for example, around more metal-rich stars, it's much easier to form those cores. And you can see the giant planet occurrence rate goes up with the metallicity of the stars. So these 2 points are evidences supporting these traditional stories of how planets formed. But as we now know from more and more studies, this story seems to be falling apart. The events came from this group of planets, which I call Kepler planet. These were discovered by the Kepler mission. Even though Kepler discovered a lot of planets, all these colored dots is Kepler discovery. The majority of those discoveries focus on this region, which we did not expect to have any planets whatsoever. This is within the AU from the sun, and with the sides, because these are transit missions, so we only know the sides, going from 1 to about 4 Earth radii. Here it's plotted as mass, and that's terribly confusing because we don't know the mass. Okay, so it's really some kind of translation. You can probably use Google Translation to translate this. Okay, so we have this large population of Kepler planets, and I'll be focusing a lot on their properties, what we learned from Kepler. Okay, I want to establish a number first before I go on to discussing them. The number is the 30% number. This is how many stars actually have any kind of these planets. We now discover a large number of these planets, thousands. And you can do a very simple algebra. You can say, well, if you discover this many planets, let's say every time you discover one of these planets, you can account for all the other planets you did not discover, but have the same property like this one. But you don't discover them because they are not transiting, or because it's very difficult to detect them. So the so-called completeness in detection. So you account for those, and then you figure out how many planets there should be there in the universe that you didn't discover, but you discovered one of them. When you do that, you find out very easily to find out this number, we're saying, well, it turns out about 100 billion planets in the Milky Way, same as the number of stars. We learned that very early on, but that's actually not the most interesting number. Because I'll give you two extreme scenarios. Okay? You have one scenario where, indeed, every star hosts one of these Kepler planets. The other extreme scenario is that you have 100 billion stars in the Milky Way, and only one star has 100 billion planets. As you can see, that's very different inferences for planet formation. So really what we'd like to know is what percentage of stars have this kind of planets. And the number we want to get to, my preferred number is 30%, but as you can see on the market, there are lots of numbers with error bars sometimes so small that it's totally screw every other possibility. But all these are based on assumptions. They have different assumptions that come in. So I have assumptions too. I'll explain my assumption and see how you buy it or not. OK. The reason this is the occupancy number is not that straightforward to get to is because we don't know intrinsically each system how many planets it contains. Okay? The so-called intrinsic multiplicity. That number is hidden from us because all we see is that in transit, we see a transit multiplicity. We see how many planets are transiting the star in that system. But we don't know intrinsically how many because there's another variable in here, which is that how spreads out, how non-coplanar those systems are. These two things kind of degenerate, the underlying and the inclination dispersion. You have to somehow break them apart to be able to figure out what's the intrinsic multiplicity. This is the Kepler, some sort of statistic. The blue bar represents that, for example, this is 1. That means in that system, we only observe one transiting planet. There are lots of them where we observe only one transiting planet. The green bar, however, represents the so-called TTV. That means that even in that system where you observe only one transiting planet, its transit is actually not perfectly Keplerian. It's undergoing variations from period to period. And that's because it has some hidden companions, typically near mid-motion resonances and perturbing it. From this, we can infer that, wow, there's actually, even the single transiting planet probably is in multiple systems. And whatever model you put in, you have to explain all these numbers, so how many are actually observed to transit and how many of them have transiting companion. So this is our assumption. Our assumption is sort of summarized by that one single formula. We say, well, nature produces a lot of different kinds of planetary systems with different intrinsic multiplicity. That's this K thing. Okay, K goes from 1 to, I don't know, typically 10 probably. And each one of this kind of system probably going to have different dynamical properties. We know that from early on, there's phrases like Kepler dichotomies floating around saying a Kepler system don't seem to be just one kind of system. They seem to have a diversity of dynamical property. But by dynamical, I meant, for example, how eccentric the orbits are and how coplanar or how inclined they are relative to each other. So we're just going to assume a single relationship. We assume that if the system has very, very few planets intrinsically, it's going to be very non-coplanar. And reverse is true for systems which have lots of planets. Okay, if you have a lot more planets, then you better be more coplanar. That's our single assumption. I would say this assumption, compared to some other assumptions, is a little bit better justified because we actually have some observed data on this, this inclination dispersion. Actually, the data I'm going to show you is not inclination dispersion. It's actually eccentricity. You can actually have some statistical measurement of the orbital eccentricity of the planet. So this is the eccentricity, typically, as a function of the intrinsic multiplicity in the system. You can see there's kind of a negative power law. This is by this data is obtained by looking at the transit durations of those planets, and so we're doing it as a statistical sample. So we have some support of this assumption, and there's also some sort of other consideration to suggest that this may be correct. Is that, well, it's likely, at least I think, likely when Kepler system was just formed, there were probably a large number of planets formed in a given phase space. And then many of these actually undergo dynamical instability in the sense that the orbits are just tiny a little bit too close to each other. And after billions of years evolution, they slowly diffuse and become orbit crossing. And once they become orbit crossing, a lot of mergers happen. You reduce the number of planets in the system, and you also make it more dynamically excited. So that's another justification. With this single assumption, the rest is just algebra, but Scott and Subodong invented some very smart algebra, which we used in this work. And from that, we infer that typically the multiplicity in the Kepler systems, as you see, there's a spread of multiplicity, but you take an average, it's about 3. And combined with the word I said, the data I gave you earlier, saying about 1 planet per star, if the median multiplicity is 3, that just means only about 30% of stars have planets.
Stars across the HR diagram, or how should we be thinking about which?
Okay, what kind of stars am I talking about? So these are predominantly FGK stars with a smattering of M stars. That's just because of Kepler's ability to detect those planets. Okay, but there's another question asked about the stars is that, what kind of stars are these? These tend to be the more metal-rich ones. It's a fair question to ask because Kepler planets contains a lot of solids within them. Okay? If every one of them have about 10 Earth masses, and I said about typically 3 planets per system, there may be even more, some even destroyed, that implies a very large mass budget. I just compared this against the mass budget in this entire minimum mass solar nebula, that kind of the model that theorists really love to play with. In that model, that we have about 60 Earth masses of total solid material, but much of those materials are actually ice, which probably doesn't condense within the AU, where we see these Kepler systems. And much of those actually in the outskirts. You can see this, most of the mass is actually distributed in the outskirts. We see the Kepler planet in the inside. So this mass budget is actually very severe for Kepler planets. So it's naively you expect to see them only around metal-rich stars. Ignore the orange line. That's giant planet, which we already know have a very strong metallicity dependence. The blue line and the black lines is comparing with and without Kepler systems. Tiny bit of difference. Statistically, you can say it's somewhat significant. You can do a better model. So Weizhou did a very good model in actually splitting the stars into 3 metallicity bins, and then do the same analysis as I said before about the 30%, and then check what's the occurrence rate or occupancy rate of planets in different metallicity bins. This is definitely a positive slope. But it's a positive slope in a very weird way. It's a positive slope in such a way that the occurrence rate goes like metallicity sublinearly. Very weak. Well, you know, when I talk about mass budget or talk about formation of planets, you naively expect metallicity really comes in strongly, right? Because the more solid there is, the easier to conglomerate, easier to grow core. Any sublinear relationship is suspicious. So I'm actually going to give an alternative explanation for this sublinear relationship, not in the terms of formation, but in terms of something else. This is wild gas. Well, it's a gas, okay? So open to criticism. I actually think this sublinear relationship has something to do with another population of systems which are called closed binaries. What's closed binary? Well, this is not really tight binary, not really far binary. This is a binary less than about 50 AU in separation. If we take a look at those kind of binaries, so this is first look at this graph. If you take a look at this kind of binaries, it turns out they have a very strong metallicity dependence in the sense that if you're metal rich, those stars have about 10% of chance of being in one of such binaries. But then as you go to poorer and poorer systems, the probability of one star being in such close binary goes up to 60%. If you keep on going to POP3 stars, you're probably going to go to 100%. So close binary prefer metal poor systems. How does that come into Kepler's? After the Kepler catalog was published, Adam Krauss and collaborators did the study. Because we just see the planet transiting the star, we don't really know that star is a single star or a binary star. So you can go do imaging studies and find out. Okay. This is the projected separation of those. If if there is a companion, this is the projected separation between the two stars. And you can see that the Kepler's planets have no problem. They sort of this is the overall binary distribution. The Kepler planet have no preference or has no information about the boundaries if they're very far apart. But if the boundary is less than 50 AU or so, there's a dramatic shortage of Kepler systems. Another way is that Kepler planets want to avoid close boundaries. Now just combine these two pieces of information together, that can explain the mild metallicity dependence. So this is how I sort of see it visually. This cyan bars or light blue bars are the Kepler systems. I just told you they have sort of a sublinear relationship with metallicity. But this is a very narrow metallicity range we're talking about. Unfortunately, we don't have. Maybe tests will give us more data on the broader range. At the moment, it's a very narrow range. It's a sublinear relationship in there, and the purple bars are the close boundary fraction within that same range. The two are complementary to each other. Questions?
What about errors? I mean,
yeah.
Metallicities, different observers get different results for metallicities on a given star and so forth. Count for that?
Yeah, so
Secure,
not secure. I think all we can say is that the number looks, so for example, the metallicity in the Capra system is using Ramos and Chinese and the Californian team's metallicity dependence. For the boundaries is from a different source, so they may or may not be completely coincident on each other. But I would like to point out that the number worked out close enough that it makes you suspicious. Close boundary have some roles to play. And the next slide I would like to show is that why I think that is so. Statistically, this is not a strong point. Yeah, go ahead.
So I think occurrence has also been shown to, well, the average metallicity of the star rises with the orbital period of the planet. That is, the planets with periods less than 10 days, those hosts are elevated in metallicity compared to longer period planets in the same time.
I do not know that result. Yeah, I think that.
Is it a strong effect? Or?
No, it's the same kind of amplitude as what we're talking about here.
I'm confused about what you mean by close.
Yeah.
In your bottom diagram, you're showing an effect for periods less than a few hundred days.
Yeah, so ignore,
Top
yeah.
diagram, it's for separations less than 100 AU, and for cosi, it's less than about 6 days. So maybe you should
Right, I
define
know.
close for us.
Close is this one, 40 AU, 10 to the 4 days. So it's not terribly close, yeah. Okay, why is that 40 AU interesting? This is a possible rationalization of that result. Okay. For boundaries which are less than 40 AU also, there's another thing that happened to them. Phenomenologically, you see that very early on, even at the sort of million years or 2 million years age, very few of them have disks around already. They already destroyed the disk, circumstellar material. So this is the fraction, disk fraction among those close boundary. Far away enough boundaries, they don't have the same, they don't suffer the same destruction. In comparison, that's a disk fraction for single stars. So we now know that close boundaries probably formed by some kind of gravitational fragmentation in massive circumstellar disk can destroy the resident disk very rapidly. They can destroy it so completely, even down to an AU, and even closer than an AU, in such a way that we see that the spin of those stars are also affected, in the sense that close boundaries, when they were born or when they were young, tend to spin faster. So that's really evidence that they destroy the disk all the way down. If that's the case, obviously you cannot form the Kepler system. So this will explain why avoid each other. As the next step inference I want to make is that, well, we also know the close boundary probably formed in some of the most massive circumstellar disks, because I will talk about gravitational instabilities. And you need to form something which is comparable in mass to your primaries. If that's the case, what does it say about the Kepler system? And why? How could this possibly explain their metallicity insensitivity? this is my suggestion. My suggestion is that the closed boundary is probably formed in this kind of systems where the disk mass to star mass is almost all the unity. The next decade, probably the Kepler system, solar system, minimum mass solar nebula, and smaller mass. So Kepler system probably preferentially formed in a very heavy disks. So heavy, for some reason, they ignore the metallicity altogether. It's not important.
What do you mean by a heavier light disk? Because all of the material came through the disk.
Yeah, it's a good question. In the star forming early stages, all this mass transported through the disk. You can actually contain solar masses in the disk. So this is probably in the sort of the last stage. For some reason, when the rapid accretion has stopped, there's a bit of a longer lasting stage where accretion slowed down and this lives a little bit longer. I can't put my fingers on exactly, but we do know accretion changed behavior. Accretion rate changed behavior. So this is now in the sort of type 0, class 0, class 1 phase. Okay. Closed boundaries. Sounds a little bit fishy. I'm open to discussion, and perhaps there's more stories that can be told. This is just an early suggestion. Let me talk about something else, okay? It's somewhat related. I just said that Kepler system avoid closed boundary because closed boundary disturb the disk. What about Jovian planet? If you have a Jovian planet, gaseous, massive, outside, do they use up all the solid material that you could use to build Kepler system? Do they dynamically disturb the formation of the Kepler system? Let's look for correlation. So Wei Zhu, postdoc in CETA, and I started to do this work with the hypothesis that if you have Kepler system, you're not going to have outer giant planets. There should be an anti-correlation between the two. Our guess was totally wrong. This is what we do, okay? Our idea is that, well, we are not observers. We have to use other people's data. So we go into archival radio velocity database, and we say, well, every time you can detect one of these low mass planets, this is period versus mass. Every time you detect this, the RV position, this is the RV position line. RV position line in such a way, slanted in such a way that you have no problem detecting outer giant planets. So let's just count systems which have those inner planets and see how many of them have outer giant planets. And we did that. The result is a third. What does a third mean? Compared to a giant planet average occurrence rate, 10%, this is 3 times higher. Later on, Heather Knudsen and her student, also Martha Bryan, also did a similar work, but more targeted at Kepler planets and looked for the presence of giant companions around them. Again, get the same result. If you have a Kepler system, chances much higher to have a giant companion. As I said, that's against our intuitive expectation. The story doesn't stop there. I'll give you 15 seconds to play with these 3 numbers in your mind. In fact, I rounded them off such that you can play with them very easily in your mind. If you see these 3 numbers, somebody want to shout out what their guess is? You can get a prize.
10% is a third of 30%.
Exactly. I got an email from Wei at midnight. He sent me an email saying, I want to write this down in case I forget tomorrow. That sums up. Let's look at it a different way. Those 10% systems that have the giant planet, statistically, 100% chance of them, 100% of them will have inner Kepler systems.
Except ours.
We are so special. We gave a price tag about 1% for our solar system, so in our paper. This is surprising. Remember I gave you the story, it's about giant planets form outside the ice lines, and they form there because there's more solid material, and they form around metal-rich systems. This doesn't make sense. In fact, this data says that Kepler systems, the Kepler planets, those little potatoes, are the ones which form in this neighborhood. They have no trouble collecting material. They formed. And only after they formed, perhaps, you have some chance of forming giant planets on the outskirts. In such a scenario, what's so special about Iceland? Because you have no trouble collecting planetary cores anywhere, even in the 1 AU or 0.1 AU neighborhood. You don't have to go to the Iceland to collect solid material. That's the what about the solar system question for you. We don't know what's wrong with the solar system. This is unsolved problem.
This is the statistics of the planets, but not including their masses. The masses of giant planets, for example, is a function of period. It would be nice to see another dimension in this statistical argument. There's a preponderance of certain mass classes.
This is mass class, that's right. That's mass class. And the relevant mass we always want to compare is a solid mass. In that sense, the Kepler systems actually don't have very different solid mass compared to giant planets. Because Jupiter and Saturn, Saturn's core for sure is 20 Earth masses, which is not that different from Kepler systems.
I'm just saying that there may be some, the Iceland may be relevant because there's a lot of oxygen. And so you might have more mass to deal with through similar processes. I don't want to divert you. It's just that aspect.
It's all question marks at this moment. We don't understand statistics, but I would argue the core mass is not very different between these different systems. Probably something related to gas accretion that's different on the outskirts than inside.
And what about the eccentricities of these
Kento is doing this. Kento is hiding somewhere. Sorry. Kento is doing the study to understand the eccentricity of those. So RV says that many of these planets are very eccentric, probably related to some kind of planet-planet scattering event. And then how do they affect the inner system? It's a big deal. Yeah. But now we know 100%. You know, if you have a giant planet, you have to have an inner system, so the connection is very tight. Okay, this is, I'm not going to go through this very long, just to show that there's another way to get to the same problem. So there's another way of getting the same problem. So Kento and us, we both do some studies by looking for, forget about Kepler system. Let's go to the Kepler database and look for systems where they have outer planets transiting. So this is very hard in the Kepler database because this planets only transit once, if you're lucky twice. So it requires very high signal to noise. When we do such a search, we tend to have very low efficiency. And guess what we found? We found some. So there's sort of single transiting planets that we found. Many of them are larger than Kepler system because the signal to noise for them is better. The surprising thing is that after we found those, we draw the lines inside and ask how many of them have Kepler systems? About a third of them do. So this is a step back, right? If you're alien looking at the solar system, you see Jupiter transiting the sun, you ask, what's the chance I'm going to see the terrestrial planet transiting the sun? Chance is much less than unity. Meantime, this says that in the other systems, every time Jupiter transits, chance of seeing the terrestrial is very high. Excuse me, not terrestrial. Inner systems are very high. And therefore, every time you have one of those, chance of having the inner ones, 100%. So this is a different way of looking at the same problem and getting to the statistics. Relative inclinations. No, relative inclination is 5 degrees. So the fact that Jupiter is already transiting already up your probability, but because inclination is not perfectly coplanar, it's still not unity observing it. It's actually something like 5%. Okay, so I hope to convince at least this part. I'm a little bit more convinced that giant planet is intimately related to the Kepler system, probably causally. Exact what the causal connection is to be understood. Now I'm going to move to a different part. So I gave you a couple sort of, I hope, interesting observations about Kepler system. Now I'm going to throw another wrench. I hope that's the right phrase. This is the Kepler system. The planet plot I showed you before, and I told you the masses are all wrong because it's some kind of random translations. In fact, I want to show you what the mass is all just lying on a single line. Another way to say is that there's some evidence suggesting Kepler planets all have the same mass. Okay. The reason that this may be of interest is because in this field, once Kepler planets were discovered, theorists, I don't call myself a theorist anymore because I'm doing observations, but theorists have been fascinated and frustrated by this problem called type 1 migration. Right? If you put a planet there, and we now know those planets are probably formed when the gas disk is still around, you can calculate the gravitational interaction between the planet and the gas disk. You find out it's going to excite waves. As a result, it's going to lose energy and shuttle into the star in about 100-year time scale. Okay. So hopefully, we can solve this problem at some point. We're not there yet. Let's see we're in the right direction. Okay, so this is about the mass of Kepler systems. Initially, this is a little bit of an involved story, so I'm going to take a few slides to explain the sort of the logic that lead to that conclusion at the end. So this is the first slide of the story. This is the, by now, primitive data from Kepler, primitive because now the data has been much improved. But back in 2016, this is what we have of the Kepler systems. They occupy close to the star. The size is, as I said, between 1 and 4 radii. This is all the data we have a lot of questions about what they are. What's the composition? Do they have a lot of water in them? Do they form inside, form outside? What's their masses? But looking at this plot, it's very hard to get any information whatsoever. Some hints are appearing very, very gradually. This is one of the hints. In fact, I was misled by this hint for a long while. This is one of the first hints. If you plot the radius of these planets versus density. Density, because back then we can actually measure a number of those planets' masses. So I prefer density over mass. So if you plot density, you can see where those planets lie at. The yellow points are the RV, radial velocity, very painful work. And the blue and red points are from so-called transit timing variation, which is just perturbation between planets, and you can measure the masses. You can see every TTV point has a huge error bars, because we have some degeneracy we couldn't really break. But together, they tell the same story as the RVs. Okay? In the sense that if you have smaller planets, they're denser. I plot the density for your human bodies on there too. You can see the planet's not that different from you. But some of them are very dense. The composition of them has to be explained if they're almost completely rocky or iron. But some of them have very low density, big fluffy balloon. So plotting this alone doesn't really tell us what's their true composition because there's degeneracy.
If you extrapolate down to smaller planets, Mercury or Mars don't fall on this trend, do they?
Oh, Mercury and Mars. No, so this is, right. So Mercury and Mars is Gen 2 planets. This is Gen 1 planet, that's the first thing. And the second thing is that density actually, for smaller planet, doesn't keep on going down anymore. Excuse me. Yeah, you can see that, for example, for water, a planet made of completely of water, what a nice fantasy. The blue line, if they are very small mass, they have certain density, which is 1, and it just stays at 1 as you go to smaller and smaller mass. But then as you go bigger and bigger, they can actually compression effects set in. They can actually get denser and denser. A water planet can be almost as dense as iron planet. Okay, so that's a fairly hint, but as I said, I was misled to something else. There's more hint coming in as once we get more TTV planets masses. here there's almost 200 of them. But now the axis here changed a little bit. This is still density, but this is actually now plotted in orbital period. As you can see, there are a couple trends emerging, and they can be summarized by just these two arrows. These are the trends that we actually observe. If you're very close to the star, those planets tend to be smaller. You can see they're smaller and denser. Smaller and denser, somehow intricately related. And if you're further away from the star, like 10 days and 30 days or so, they tend to be bigger and fluffier.
This has been corrected for selection effects.
Um,
The closer ones transit more often, and so you detect them at smaller sizes.
So the completeness of this kind of planet lie, at least within 30 days, is a bit much lower than what I'm plotting here. So yeah, we complete in those. Let's imagine every planet is the same. They had a core, some 10 Earth masses or so. And each one of them, when they were born, they were all endowed with a couple percent of hydrogen and helium. That simple hypothesis, so they were called mini Neptune. The simple hypothesis can explain this trend, because if you're just adding the correct or observed amount of X-ray illumination on the surface of this planet, X-ray and UV can hit their atmosphere to about 8,000 Kelvin, surface to 8,000 Kelvin, and that's about the escape velocity from those surfaces, so you can drive a Parker wind. Over time, you can boil off the envelope if you're close enough to the star, making those very small and dense planets. So that's the hypothesis to explain the trend that we observe in all these mass measurements. Lucky for us, this was very soon the California team provided evidences for this hypothesis. So this is the evidence. In the model we make for this photoevaporation, I don't know if you can notice, but I make sure you know this because I put a blue bar in between. There's a big gap, small gap actually. As a gap, okay? That's in radius versus period. So planets in those phase space, what they have is that they have smaller amount of mass than the one a larger radius, but their radius hasn't gone down so small, they actually receive proportionally more X-ray and UV flux than the ones up there. So once a planet goes from above there, losing mass, and goes through this gap, they're going to lose mass at some enhanced rate, and they very quickly sweep through it. In the model, we're going to find there's a deficit of planets there. This is the data when the error bars is reduced by a factor of 3. So it's probably correct. It's probably photoevaporation that's causing the distinction between super-Earths and mini-Neptunes. And with James Owen, who was a postdoc here in this building, we did some modeling trying to understand what kind of planet parameters can give rise to the observed feature. And we found out that, well, indeed, if this is a super-Earth, if you give some masses to the planet, this is a super-Earth because they become bare, they lost their envelopes. But then at about twice the radius, the remaining planet will be clustering around here because they have about 2%, and those 2% is very hard to boil off. And there will be sort of a bimodal distribution in size. And that probably explains the observation reasonably well. And that's enough about photoevaporation because it's like Kozai. I can't talk about it anymore. It's so I have nothing. I don't want anything more to do with photoevaporation until 2 years ago, until 2018, last year. Gaia released its data. In 2016, Kepler's photometry data is based on stellar radius coming from some kind of broadband photometric determination. You can see the error bar there is bigger than 10%. So as a result, any feature in the size distribution of planets got smeared out. The second panel is the so-called California Kepler survey, the one I mentioned briefly before, where they're pointing the big, powerful CAC at the host stars and getting high-resolution spectroscopy, and therefore determine the size of those planets and beat down the error bars by a factor of 2. 2018, Gaia released its general second catalog, And for individual stars, the error bar has gone down even further.
That's because you have a proper luminosity?
And because you have a proper distance, right? You have a luminosity, and then they use a homogeneous way of determining the temperature. When I first saw this figure coming out of Gaia, I was really stricken by how narrow those peaks are. As now you probably have a feeling that the size, the distance, sorry, the position of those peaks corresponds basically to the mass of the planet, right? Assuming we know the composition, which every determination up to now is hinting that these compositions are terrestrial, like rock, basically. So this is really just mass measurement. So you can see that some sort of is floating up to the surface that these Kepler planets seem to have the same mass. These ones at twice the radius, they also have the same mass as this, they just have a hydrogen on top. Even more surprising, when you plot these sizes of these planets as function of the host star mass, actually host star radius, but let's think the mass, stellar mass and stellar radius is the same thing. This is a super-Earth clump. That's twice the radius, sub-Neptune clump, or mini-Neptune clump. Both population. I hope I don't want to convince you there's a scaling there. There's a correlation there. This is the Gaia data. I have to supplement Gaia data with some ground-based M-dwarf data. So it turns out Gaia wasn't that great for M-dwarf. It couldn't really determine M-dwarf radius using the black body law very well. So there has been a lot of effort using empirical spectroscopy calibration to figure out M-dwarf radius and so on. So I combined the two data sets, but still they fall on the same line, saying that it looks like those peaks that you saw before, they actually really depend on stellar mass. Obviously, you have to going back to the model, photo vibration model, and try to do some simple modeling to see how best to explain that. So this is the same data. I split the radius. This is, again, radius of the planet, and then I split it by stellar masses. You can see those peaks are systematically moving to the right as you go to higher and higher mass stars. And then now it's this very simple process, right? How much do I have to change the radius, scale the radius such that all the peaks are on top of each other, like this? That's the result. I have to scale the radius by, I have to scale the mass of the planet in such a way that it scales linearly with star mass.
Does it correlate better with stellar mass or with stellar insolation?
Okay, so stellar, you mean total luminosity, or you mean?
Well, no, flux at
yeah,
the planet.
right. So that's so as you can see in here, right? So this is the orbital period. These two clumps are separated at different locations. This is super-Earth clump. They have to be close to the star because we need the starlight to rope them off the hydrogen. So insolation does affect the size totally, but that's for the reason that it's easy to take account of. What I'm saying is that you need actually also this clump, this position of this clump actually moves upward for more and more massive stars. And you actually have to take that into account to be able to Does that answer your question? If you're not following. Okay. I think the simplest way to look at it is that if you look at just the size distribution, forget about distance, then the size distribution has a systematic shift to larger and larger size with stellar mass. As I said, size is just mass. So that means bigger stars host more massive planets.
More massive stars have a radii, which proportions are larger.
Mm-hmm.
So
Mm-hmm.
fixed radius will call it less of light. So
Yeah. actually, I shouldn't have deleted it. So there's, Scott asked me the same question last time when I gave a talk. There is a selection effect that it's easier to observe larger planets around larger stars because the fractional accounting light is the same. On the other hand, there's a compensatory effect because larger stars are brighter. So we can actually get down.
But it's a magnitude selected sample, so.
No, but it turns out even in that magnitude selected sample, the larger stars are brighter. So we actually did the careful completeness correction. Well, I did what I can, completeness correction, and show this is not a selection effect. Yeah. This is a really, this is a very important point, though. I hope somebody else will repeat and actually say something about this. Yeah. Okay, so let me summarize this, what this story is leading us to. Those peaks, the super-Earth peak and Neptune peaks are narrow. Currently, they have certain width, and you can fit them with some kind of Gaussian profile, or the Gaussian profile such a way that most of the super-Earth is born within factor 4 in mass to each other. So this is for cosmology. I don't know if any cosmologists here is saying, well, all the galaxies in the universe has to be born within factor 4 in mass. It's very bizarre. We know this has to be true. This spread has to be small because otherwise we wouldn't be able to see those dips in between the two peaks. They're going to be smeared out because there's a dispersion in stellar mass and dispersion in planet mass going to spread out those peaks. This factor 4 spread is much smaller than any other intrinsic spread you can think of. For example, metallicity between stars, mass of the protoplanetary disk, anything else you can think of that the environment has a much bigger spread than factor 4. So there's something very special about that mass. There are even some evidences that the spread's even narrower than the factor 4 we obtained. This is the Gaia data, but then overplot on top of it is some other data from seismology. Even smaller data error, even smaller error bars, you can see the peaks got even narrower. Or you can split the planet into different populations, and you can get even narrower spikes. So it looks like the Kepler planet that we see there, they all have the same size and same mass. I will also say it's very surprisingly that the hydrogen envelope mass, which is correspond to this peak, if you have a big spread of hydrogen envelope mass from 2% to 20% big spread, you're going to get a very broad peak. You don't. So that again tells you that even the hydrogen mass is very, very narrowly spread. Associated with it, we don't have any evidence that any planet in the Capra data catalog, well, we don't have any evidence that significant population of them is born without hydrogen envelope. There's no Earth.
But this says more is that there's a narrower spread of radius than the mass.
Much narrower than spreads in metallicity and disk mass.
Mass, and you're talking about radius, but the spread in mass would be wider.
So no, I'm talking about spreading mass. The radius is mass to the quarter power.
Yeah, exactly.
Right.
So a certain range in radius would be a larger range in mass.
So this looked like a big spread to you. Okay, this looks like a big spread in radius. On the other hand, remember I gave this correlation before. This depends on stellar mass. So if you take away the stellar mass spread, this peak narrows way significantly, and that's this factor 4 is from modeling that. I'm running over my time, so this is my. Okay, I still have 3 slides. Sorry, I hope you have enough patience for it. This is my so-called interpretation. What's so special about that mass? Took me a long while because I don't work in this field, this planet interaction. I didn't work on it much before. So it took me a while for this concept to float to the surface, is that there is a special mass in protoplanetary disk, the so-called thermal mass. That is that if you have a disk surrounding the star, the disk has certain pressure scale height, and that pressure scale height defines a special mass, which is, if you set the pressure scale height to be the Hugh radius of the planet, you get a mass out. And that's described in that formula. So if you happen to say, well, if every disk around stars have scale heights, vertical scale heights 2%, then they should all give birth to planets. Well, and if they all make planets exactly at the thermal mass, then explains the observation. You see the two if there. Neither of this if we really understand. I just give you a range of theoretical proposal, including some made by the people in these rooms and so on. You're not meant to read through it, but see that there are actually a large number of theory proposals. And the role now, I guess the task now is to see which one makes more sense than others. Why the thermal mass enters into making generation 1 planet.
Putting aside on the theory here,
Mm-hmm.
if you re-express this in terms of, H of course is related, H over R is related to the temperature.
Yep.
And of the gas.
That's right.
The mass of the central star.
That's right. Why should they be all this?
Express it in
Mhm.
terms of stellar mass and temperature at the position of the planet.
So I didn't explain this thing. So you can make different disk model depending on the stars, depends on luminosity of the star, mass of the stars, and depending on whether the disk is accreting or not. So there's no reason to expect the H of R is going to be constant. Exactly. I do say there is one class of disk which is a little bit better suited for this purpose, which is the passive disk. This which is not accreting, and turns out if a disk is not accreting, the H over R, in which the stellar mass and stellar luminosity, stellar heating, turns out cancel in such a way that H of R is roughly constant. I don't expect H of R overall to be constant. But the data is suggesting that if this is a thermal mass, if this interpretation is correct, then there's something special about those disks. My last 1 minute, I'll make a pitch. All this talk, I haven't touched on generation 2 planet, which is the one we're standing on. Where is the generation 2 planet in Kepler database, Kepler catalog? We already took away the mini Neptunes and super Earths and say they were forming disks. They had hydrogen. They were massive. They somehow know about the disk. So where is the population of planet which were formed after this gone away, and you have perhaps some residual material left in the disk, and then conglomerate, have giant impact, and in the end form into Earth? There's very little evidence in the Kepler database, right? Mostly because signal to noise. There's some evidence, there's some population of planets here, which I call the sub-Earth. There's a little bit here, little extension here. They're heavily incomplete in the Kepler search. The number could go up dramatically. Unfortunately, Kepler just falls short of telling us whether they're there, are they separate population, how many there are there. If you're funding agent, funding agent also love this green box. For that, currently we have 0 candidates. The 2 missions, one is already well known, and because it's already underway production, the European Plateau mission, which is exactly looking for those smaller planets, perhaps longer periods around stars, solar type stars in particular. Just in case they don't succeed, we proposed another mission, which for the moment we call Super Kepler. This is going to be staring at the Kepler field for at least another 4 years, and probably neighboring fields. With the wonderful help by Chelsea Huang, who was a student here, we were able to make some predictions of how many of those small planets we're going to be able to observe. Out of those 1,000 ones, about few of them potentially could be in the habitable zone, depending on the model.
When you have photometry, or just is it big light bucket?
It's a light bucket, it's a photometry.
One band.
Yes, broadband. But once you find a candidate, you can do whatever you want with it.
That's in your book.
Yeah, so this telescope is not, it's only for discovery. It's not able to do any kind of characterization. I'm summarizing. This is the cartoon I want to leave you with. Hypothesis is that the Kepler planet, the generation 1 planet, forget about the giant planet. They're just a little, appendix. The Kepler planet is the majority. They occur about 30% of stars, and they probably form around they form probably around the more massive protoplanetary disks in some close relation with close boundaries. Within those Kepler systems, we now know many of them contain multiple planets, and they contain all the giant planets we know of. And we also know their masses are very uniquely determined. This is my last punchline, is that we're now going for the next go. Thank you.